pieces here at the TFA. So they arrive here essentially fairly green in terms of research, having done just a small research project in their degree so far. And some of them have sort of arrived without even using Unix, for example, or without having done any sort of command line sort of work or anything like that. So it really is a ramp up and then into a research project until it's time to start writing the pieces. So it's a very fast program, essentially 8 months to get all that done. So they come here, and of course they're thrown into the US culture, and what they've missed while they've been in the US is 3 prime ministers. There have been 3 prime ministers while they've been away. There have been 2 monarchs. That doesn't happen very often. The recent coronation, and of course, maybe some of them are a little bit sad about the demise of Arsenal's Premier League campaign this year. But okay, so without further ado, let me start. Essentially, they have to now do their final thing. This is their last formal thing they have to do before they go home. And it's sort of, I suppose, running the gauntlet of this vicious, cruel audience in the pioneer lunch. So first speaker, big tip speaker, is Jessy Marin. Jessy was actually born in Paris, but he's also lived in Shanghai and Thailand, in Bangkok, during his early years. He has other hobbies outside of astronomy, which include sewing and cooking and jigsaw puzzles. He also plays basketball and a new sport that I hadn't really heard of called canoe polo. Interesting. And during the summer, so after this, of course, they have a nice relaxation summer, some of them, but Jessy's going to finish his current paper and go camping in Wales and finally spend time with his family. Now, what else do we have? What he's going to do next year, he has a PhD position at the University of Manchester, working on simulations of magnetic fields in giant molecular clouds. And I always ask them, what do they find striking about the US? And Jessy was the landscapes and the big trucks, and why are there so many flags around? And what do you miss most about your home country? Cheap beers. Well, I can identify with that one too. But the most amazing thing about Jessy is that he got engaged two days ago. So congratulations. And he's going to be calling today on magnetic properties of a star-forming galactic bone.
Can you guys hear me? Is this working?
No.
No. Wait.
They need turning on me.
Oh, okay. Is that good? There you go. Can you guys hear me now? Hello? Oh, there you go. Okay, cool. Awesome.
The angle. Yeah.
Well, hi everyone. Today I'm going to present my research, which was led by myself and supervised by Philip Myers and Ian Stevens in the audience right now. So our galaxy, the Milky Way, as you probably all know, is a gigantic, beautiful, and messy radiant disk of gas and dust. And we've known now for about 70 years that our galaxy is a spiral with 4 arms where all this gas and dust are mostly concentrated, and those arms are also where most of the star formation in the Milky Way are happening. In 2015, Zucker et al. Identified a series of thin, long, and very dense IR dark clouds lining the center of each arm. These clouds were labeled as galactic bones, as they delineate the densest parts of the galaxy. In the 8 years since their discovery, we've been able to determine a lot of the physical characteristics of these bones, but still one open question remains for bones and the Milky Way at large. What is the role of magnetic fields in large-scale star formation? Here I have 2 images of 2 physical images of 2 of the bones, so you can see them there. They're really pretty. So we know that magnetic fields are dynamically important in star formation. It's been shown that fluctuating magnetic fields have an energy that can be up to roughly 60% of the turbulent kinetic energy, which equates to a pressure support that is roughly 30% of the pressure support due to turbulence. This essentially means that strong fields can prevent gravitational collapse, which has tremendous consequences in star formation. One thing to know as well is that under ideal magnetohydrodynamics, field lines are said to be flux frozen, which means that the magnetic field stays within the magnetized medium, which allows us to trace the movement of the gas. this means that if we imagine a medium of uniform density contracting into itself, originally parallel magnetic field lines are going to be dragged along with the gas and form this hourglass or pinch field morphology, which has been observed before. And Myers et al. 2018 created a model with a number of simple assumptions, such as flux freezing and mass and flux conservation, which finds the resultant field morphology and field strength by fitting the initial and current conditions of the condensations that we're observing. This actually allows us to get estimates of field strength at the core of these condensations, which are relatively hard to do. We know that magnetic fields are traced by polarized dust emission. However, this does not give an idea of the field strength itself. To do so, we can either do direct measurements through Zeeman splitting or use indirect measurements such as the Davis-Chandrasekhar method, which is the most commonly used method, which relies on the assumption that turbulent motion of the gas will excite what are called Alphen waves in the field. A great analogy is if we conceive of the field lines as taut strings that are perturbed by the turbulence in the gas. The higher the tension on the string, ergo the higher the magnetic field strength, the lower the perturbations that are caused by the turbulence. And so by seeing how wiggly the fields are, we can get an understanding of an estimate of the field strength. And so this project is part of the Field Maps Legacy project, which is the only one of its kind, and is made possible by the use of the Hawk Plus polarimeter on the Sophia telescope to map 214 micron polarized dust emissions across 10 of the 18 known bones. Unfortunately, Sophia is no longer with us, but it stays in our memory. Out of those bones, filament 5, also known as G18.88 minus 0.09, long name, stands out as being the longest known bone in the northern hemisphere. It has a projected length on the planet sky of about 50 parsecs and is 3.4 kiloparsecs away. And just to give an idea of scale, this here, that's 1 parsec. And so we're looking at a gigantic structure in the Milky Way. The red vectors here are polarization vectors with polarization factors a fraction less than 20%, and the yellow ones with more than 20%. And the green and blue dots that you can see scattered are class 1 and class 2 stellar objects, young stellar objects. And so this clustering of YSOs here and here is a good indication that this bone is actively forming stars. And as you can see, there's lots of fields happening there. And so what we do is we apply our DCF method along the spine of the bone. And so here, this top figure shows the field strength that we find, and we find that they range between 60 and 180 microgas along the bone. That doesn't mean much to most people, and so a great way of understanding of contextualizing that information is by looking at the mass to magnetic flux ratio. And so and comparing that to the critical mass to magnetic flux ratio. We combined all of this into a quantity called lambda, where lambda being less than 1 means that magnetic fields are strong enough to support the structure against gravitational collapse, and lambda being more than 1 means that there's enough mass in the bone to cause gravitational collapse. And so we find that, and so here, this is lambda along the bone, and so we find that lambda is less than 1 for the entirety of the structure, except the highest values of lambda are located more or less where we find where we have evidence of star formation. So we know that star formation is happening, but somehow this entire structure isn't critical to gravitational collapse. What we can do next is we can zoom in on the star forming region and model the condensations, and in order to get a better understanding of what the magnetic field's strength is in the structure. And so this is what the data, what this condensation looks like. Here we fit 3 former spheroids that are inclined on the plane of the sky to the condensation, and we get really a pretty good fit all things considered, considering the complexity of the model. We find peak magnetic field strength in each condensation of 300, 350, and 600, roughly 600 microgauss. And the most important thing to note here is that we find that the entire, this entire structure is again subcritical. What we do next is we compare the model, the predicted field directions with the actual field morphology. And so in blue, the blue streamlines are the model, and in red, it's we have the data, and we have a surprisingly good fit to the data. So the average difference between the model and data is of -9 degrees with a dispersion of 16 degrees. This is one of the best applications of spherical flux freezing that has been obtained so far, and so we're confident that we're able to get good results, that we have a good fit. However, we know that stars are forming in the structure, but we're still getting subcritical structure, and so it means that mass has to be coming in somehow. And so here you can see that there's a consistent deviation between the model and data. We think that this is most likely caused by flows of gas that are redirecting the field direction. And if those flows are real, flows along field lines could cause the structure to be critical at smaller scales. And so while at larger scale, the entire bone can be supported at smaller scales, because of this mass accretion, we could be seeing higher values of lambda. And so to conclude, we find that the field strength in the bone typically vary between 60 to 180 microgauss, but maybe up to 600 microgauss. The entirety of the bone is not critical to collapse, and magnetic fields are thus likely an important factor in support against gravity at these scales. And we suspect that higher values of lambda may be more localized with star formation, necessitating higher resolution polarimetric and spectroscopic observations towards the young stellar objects and density peaks that we're observing. Thank you. And last thing, I wanted to thank Philip, Ian, Simon Kude, and Nicole Connor for supervising me during this year. I couldn't have done this without any of you guys, so thank you.
Thank you very much, Jessy. So, I mean, any of you have given like 10-minute talks at AAS know how difficult it is to compress all this work and reflect the fact you've done all this stuff in such a short time. So that was really, really well done. Yeah, we have time for a couple of questions. Let's see, first Roseanne, and then give my more Roseanne.
That was a fascinating talk. That was a fascinating talk. And you know, it's really interesting the way you're tracing through where the magnetic fields are stronger in the value of lambda to try to find the place where star formation can occur. And just looking at your images, it looked like this physics suggests that almost a filamentary structure with clumps of star formation being the standard. Is that in fact the case? And if it is the case, is it primarily because of the effects that you're looking at?
Outside of field maps, nobody's really done what we're doing. So we have done a similar analysis with the G47 bone, and we find again consistently that most of the structure is fully subcritical, and magnetic fields are fully able to resist to prevent gravitational collapse by themselves. It's like you said, we have value, it's places where there's star formation and values are from like around 1.7, where we do see gravitational collapse, and like so we have those small clumps with large filamentary structures and then small clumps again.
Thank you.
This is so interesting. Thanks. I think the root of my question is actually kind of similar to Roseanne's. So, how do you think, just in general, this sort of geometry affects things? So, when we were looking at the sort of simple models of the cores and their field, it's kind of converging to a point, and then this is a long, stretched out structure, and as you try to sort of fit the field angles and stuff across that stretched out thing, how does that affect the sort of analysis you're doing?
Yeah, and so I mean, so this is actually a really deep question, and so we know that on average, it seems like fields are perpendicular to filamentary structures.
Okay.
And so if you imagine the perpendicular fields, and then afterwards, even though you have this filamentary structure within the perpendicular field, you're still able to model the condensation because you have those fields are originally perpendicular. Why those fields are there and why they're perpendicular, I don't know, and I don't think that anybody can give you a straight answer that it can be fully confident with. But it's like this field is still new, and the bones were just discovered less than 10 years ago, and so there's a lot of like really interesting research which is coming ahead. It's a shame that we lost the field, but we're still excited with all the work that we're able to do.
Awesome. Thank you very much, Jessy. So we have a really tight schedule here, so I'm afraid at the end there's only time for a couple of questions each. So I apologize for that. We should also monitor the online ones. Yeah, thank Jessy again. Our next speaker is Ieva Jankute, who hails from Lithuania. She has lots of extracurricular and curricular activities she gets involved in, playing guitar, both electric and bass. And if you're thinking of asking nasty questions, I'll just let you know that she is a master at martial arts, including Wing Chun, Kung Fu, and Kendo. So just bear that in mind. She also does a bunch of sports in Southampton, including rowing, and she's also a pool shark, it says here, table tennis and badminton. So what's she going to do in the summer? She's going to Japan to do more Kendo, and that is with the Harvard Rapid Kendo Club. So that's sort of excellent that being able to take advantage of this sort of Harvard community as well. So Ieva's going on to a PhD in Durham University in England afterwards. And what did she find surprising during the US? It was how talkative and friendly strangers are. That's really nice. What did she miss? Friends and family and UK nightlife. Okay, that's probably getting back to cheap beers again. One thing that people find surprising when Ieva tells them is that Ieva actually failed her high school final exams pretty much. And she brought herself up from her own bootlaces through the Southampton Foundation program and came to be one of the top students in the physics class. So this is just a lesson to you chaps that, you know, if you don't first succeed, it may not be you, maybe the system. You can get there other ways. And she's going to be talking about preliminary analysis of candidate X-ray dip events.
So, hello everyone. I'm Ieva, as Jeremy nicely introduced me. This year I was working with. Okay, yeah, I have never used this before, so I'm gonna try this work. Okay, I hope this works. This year I was working with Roseanne Stefano and her group, where we are searching for anomalous events in the short duration X-ray data and analyzing them. So I'm particularly focusing on the analysis part. So I'll start by introducing this paper by Ieva and Stefano in 2018, where they suggested that one could find exoplanets by looking at the X-ray light curves of X-ray binaries. So here probably most of you know what an X-ray binary is, but I will still say it. So it's a binary star system where one of the stars is actually a compact object, so a black hole or a neutron star or white dwarf that is secreting mass from a companion star. So a planet can actually be transiting such an X-ray binary, and it can be orbiting it. And if a planet goes in front of an X-ray emitting region within our line of sight, it can block most of the observed X-ray radiation. So in fact, 3 years later, Stefano and her group published a paper where they found a planet basically using this method, where they observed a significant decrease in photon counts in the X-ray light curve, which has been photon counts over time. And here you can see these plots, both assumed version and the full observation version. And you can see that the photon counts can dip all the way to 0, which is because a planet is, in some of the cases, it can actually block most of the X-ray radiation. This is because the X-ray emitting regions are actually quite small, and they can be comparable to the sizes of the planets, which is a good thing about this method. However, due to the small size, the transit time is also quite small, quite short. So it's usually less than 20 kiloseconds. So in this project, I was using 8 sources, analyzing them that I manually selected from one of the collaborators, Seth Larner catalog. So he is a student, and he was working with Rosanna and her group over summer. So in this, he looked through all of the light curves observed by Chandra. That was around 1,000 observations in all of the galaxies also observed by Chandra within 11 megaparsecs. And he made this, he then ran the Bayesian blocks algorithm to detect anomalous events, so a significant increase or decrease in observed photon counts. And he made this nice catalog, and I selected the dips that were the most promising, that were less than 20 kiloseconds in duration, and where both the beginning and the end was visible. And then the next step was to actually make sure that the data reduction procedure is accurate. So here you can see the background regions. I actually obtained the event files and source regions from Chandra's source catalog, but I made the background regions myself. So by default, I was using a circular annulus, and you see that here. These yellow are different other background sources which have to be excluded so that the background wouldn't be influenced by it. However, in some cases, in very dense regions like next to the galactic center, we actually need to do a more complex background region. So why do we need to do so much work and make sure that the data analysis procedures is correct? Well, first of all, here I'll show some of we have found some of the dips were actually background related. So here, if you see at around 40 kiloseconds, which is before the background correction, the light from before it, we see something that was actually detected by the Bayesian blocks algorithm as a significant. However, after background correction, it's not seen anymore. Another thing is actually the dips that are due to instrument itself. So it's very important to account for the exposure, which is the time that the Chandra detectors are actually the effective time that Chandra is actually observing the point source. And it can also, because exposure might fluctuate, although it's not very common, it can also cause like these dips in the data. So we also need to account for this. Now the next part of my my project was actually analyzing these 8 sources, and I analyzed all of their observations. So some had from 1 to 30 observations each, and although. So the point was to see if the dip might be a possible planetary transit, and most of them were actually likely caused by the accretion disk, because we observed spectral variations. However, there was one that is quite promising. So here you can see at the very top, you can see the light curve in the broadbands, which is defined here. And there are also Bayesian, there also you can see Bayesian blocks, so they're also numbered here, and they are in red with the uncertainties. In the middle plot, you can see the light curves were in the different bands. And the very bottom is the hardness ratio, specifically the color, which is log of a lower energy divided by a higher energy photons. Here specifically is a running average of plus minus 16 counts at the time that a photon was incident. And so what we can see from here is that actually where the dip happens is that the color is actually non-variable, and before that as well, there's a short time when it isn't variable either. And another thing that is important just before the dip, the spectra is actually softening, which you can also see from this plot, which shows the changes in spectra, so it's color versus color. Well, and here the arrows indicate going from one Bayesian block to another. So here particularly is when we are going into the dip, we see that the spectra is actually softening. So these vertices actually indicate which an increase of which band of photons. So the spectral softening is actually also a bit unusual if due to it for dips related to accretion, and it could be possible that it's due to planet, because when we imagine like a planet going into an eclipse around the X-ray binaries. So first, if the planet, for example, has an atmosphere, it's going to be the atmosphere that is the first that blocks and in fact scatters the most energetic photons, and only the rest and only later the rest of the planet body goes and fully blocks the X-ray radiation. So yeah, so just to summarize, this year I was working actually together with Rosanna Stefano and her group, and I particularly was making sure that all the data reduction procedures are actually excruciatingly correct. Like one of the group members from IPSHAB mentioned, who is an expert in astrostatistics and was helping me a lot with the data reduction. Because it's important for our groups and to make sure that we have these steps in progress before we are actually moving into bigger samples of data, finding more samples, and hence why I also needed to do such a preliminary analysis, so that once we have this bigger sample, we would be able to quickly see whether a dip is actually potentially interesting and worth a follow-up analysis. So while doing this and while testing my data visualization methods, I also found out that one of the dips might be actually promising and worth looking into more. Thank you.
Excellent. Thank you very much, Ieva. Do we have any online questions? Just to give them a chance in case. Oh, yeah, okay. Right. Any questions? Jessy, yes, and then onward. Yes, sorry.
Really great talk, everyone. And so, what are the steps necessary to like confirm that what we're seeing is a planet? Like once you verify that the dip is real, and that it could be from a planet, how do you verify that?
Right, so the question is, how do you verify that, what would be the other steps to verify that this is actually due to a planet? Also, by the way, thank you for the question. So yeah, one of the most important steps, I think, is actually model fitting. So you make sure that it actually agrees on the theoretical aspect that such a transit is actually possible theoretically, but also it's important to do a cross match with other observatories and try to find in the other light curves whether there is another transit observed, because then we can see also obtain other parameters such as the period of the planets. Like, yeah, so it is a bit hard from just one light curve. Yeah, thank you.
Okay, very nice work. Congratulations. My question is, personally, it's very hard to imagine that the planet in the X-ray binary system, that's very hard environment, right? It has to go through the supernova explosion and so on. So how could planets survive there? That's one question. And the related question is, what if it's not a planet? What other possibilities there?
Okay, so the question is, how can a planet survive in such a harsh environment? And if not a planet, what else could be a blocking? Also, thank you for the question. So, yeah, so there have been actually observed that there are planets orbiting around, for example, neutron stars, and so also, for example, there have been around white dwarf stars. So in case of the white dwarf, the planet might survive the supernova, but most likely from the white dwarf or the neutron star scenario, it's there due to a planet capture. And another thing, or also it might have been formed from the supernova remnants, for example. Now, another thing, if not planets, so actually is another interesting thing is a triples. So there might be another star orbiting the binary star system.
Excellent. Well, thank you very much. Let's thank Ieva again. So our next speaker is Ethan Tregidga. I hope I got that pronunciation correct. Ethan is actually born in New Zealand, and he grew up in England. Ethan plays bass, drums, and guitar, and also squash and dodgeball, and enjoys live music. And in the summer, he's going back to New Zealand to visit his family, and he's going to be traveling around Europe a bit. And next year, he has a PhD at EPFL in Switzerland on machine learning applications to dark matter research. And what did he like or find surprising in the US? Well, it's basically found the CFA a great place to work. Lots of events, and he also really enjoyed the AAS, so that's great. And what did you miss about being away from the UK? And I think it gets back to the cheap beer theme, because you can say it's pubs, cheap food, and the societies that he was in Southampton, so social work stuff. Is there anything unusual? Nothing that you would like to mention, but we'll see what happens in store.
Awesome. So I'm going to be talking about using machine learning for rapid spectral fitting of X-ray binaries. So continuing from the X-ray binary thing, I'll be working more in particular with Black Hole X-Ray Binaries. So we have a stellar mass black hole that is accreting material from a non-degenerate companion star. And this accreted material will start forming an accretion disk, which has very strong X-ray emission. So the main components that we're focusing on in the energy spectra is the thermal emission that comes from the accretion disk, which we can see in blue. That just forms typical black body like spectra shapes. We have a non-thermal power law component, which comes from the thermal photons being upscattered by the hot corona. So we see the pink region is where we get the higher energy power law component. And then there's the additional non-thermal reflection component, which we see in red, and that comes from the now compositionized photons reflecting back off the accretion disk. And that has some interesting properties where we can start seeing emissions from the accretion disk, such as the iron K alpha emission line at 6.4 electron volts. And what's particularly interesting about this is that due to the extreme gravitational environment around the black hole, we can see some interesting relativistic broadening, which can help us constrain theories like general relativity. So for this project, we're doing a fairly simplistic proof of concept model just to test the application of machine learning. So we've got 5 free parameters. We've got the hydrogen absorption, which is just how much of the X-rays can be absorbed between us and the source. There's the non-thermal component. So we just have the power law spectral index and the amount of photons that gets scattered off the hot corona. And we have 2 parameters from the accretion disk, the thermal component. So we have the maximum disk temperature and the normalized flux of the accretion disk. Now, this is rather simplistic. It doesn't properly account for the different components. So future work will use more complex models, and that would also provide us more useful information about the system itself. And we're using 10,000 observations from the Neutron Star Interior Composition Explorer on the ISS. For the baseline, just to see what sort of accuracy we should be getting when we do curve fitting, we're using just a brute force method using expert for baseline. So what the current reason for using machine learning is that current methods of fitting is very slow using curve fitting software like expert, and it scales poorly of model complexity. So if we can have a new approach that instead of trying to iteratively improve your fit, we can instead just look at a spectrum, identify what features it has, and then predict parameters from that, then hopefully that can bypass all these slow computational processes. And so that's what machine learning hopes to do. So what is machine learning in a very high level overview? On the right, we see a figure that roughly outlines it. So we pass in some input data like a spectrum. We pass it into some network, which is just a large function that is differentiable. And it has parameters or weights called W. And these are tunable that we will tune to optimize the network. It will produce some outputs depending on if we're using supervised learning, where supervised is if we have prior knowledge on the parameters of the spectrum, or the spectrum itself, which would be unsupervised learning, where we don't need any prior information on the system. And once we produce an output, we can compare it to a ground truth, and that can then tell us how good was our network. And then that we can use that result to update our network to try to minimize the incorrectness of the network. And so we train this on a large data set of training data and iterate it until we can get the smallest loss possible. So the general architecture we're using is an autoencoder. So an autoencoder is where we take some input spectrum, it will compress it to a low dimensional space, i.e. the parameters that we want. And then because we don't have prior information on the parameters, we will then reconstruct it into the original spectrum. So the network's going to try to learn how to map the high dimensional spectra to low dimensional parameters and then bring it back to the beginning. And because we're reconstructing a spectrum or a pseudo spectrum, we can then train the network to minimize the difference between the pseudo spectrum and the original spectrum. Now, one big problem with this method is that the latent space or the parameters that we're trying to get in the autoencoders, this is non-physical. So it's not actually going to be the parameters that we want. It'll just be 5 random numbers that the network learns to use. So this is where semi-supervision comes in for the autoencoder. So what we propose to do is, instead of training the autoencoder in one step, we're going to first train the decoder on synthetic data, as it's very easy to generate labels for synthetic data, or the parameters for the synthetic data. So we train it on 100,000 synthetic data. And so we're going from parameters to the output spectrum. And then we're going to train the overall architecture, the autoencoder, using unsupervised learning, like the traditional autoencoder. But now, because we've already trained the decoder, this trained decoder forces the latent space to be the physical 5 parameters that we want. And then we can just do the unsupervised learning by reproducing the output and comparing it to the input to train the encoder. And we do this on 10,000 NICER observations. So for the results, to train the network, we want to try to minimize the reconstruction loss. So you can see here, this is the autoencoder's reconstructions, and this is on real data. So you can see that it is very good. It has very low uncertain errors where we want it ideally. So what we now do to actually see, because if the decoder's got a problem, then the encoder can try to compensate, which makes it look like it has a good reconstruction. So we want to test it using traditional expert fit statistics to see, is this actually a good fit, or is the encoder just compensating for the decoder? And so what we do is we use 1,000 unseen NICER observations. So the network's not seen these before. and we will use Poisson data, Gaussian background statistics to measure the uncertainty, to measure the accuracy of the fit. We compare 3 scenarios. One is just the pure encoded predictions. One is to use traditional methods of expert brute force curve fitting, and then one is to combine the 2 methods to see what we can get. So the results are here, and so we can see that the time for just the encoded predictions on 1,000 spectra is 36 milliseconds, which is very fast. However, we can see here that the reduced PG stat is not quite where we want it yet. So while we do get a 2,700 times improvement in speed when getting comparable reduced PG stat with traditional methods, in order to get the best fit possible, we have to currently combine our method with expect fitting. So if we do that with just 10 iterations, we can get to a reduced PG stat of 4.76, which is now starting to encroach upon the best fit limit. And this only takes 96 seconds. And what's interesting is if we try to reach a similar PG stat with just brute force methods, we see that it takes 288 seconds with 60 iterations. So what's interesting is that we would expect only 20 iterations if they can get similar performance at 10 iterations. So that suggests that the encoder is actually suggesting parameters that are closer in parameter space to the true parameters. So therefore, it's less likely to get stuck in local minima. So this could be really interesting when we start going to more complex models, where each iteration is very computationally expensive. So in summary, we've shown a method where we can reduce the computation time by 2,700 if we just use machine learning. However, the fit statistics are not quite where we want them yet. So the goal would be to do several methods to try to improve the accuracy. Now, one of this is what we're planning to do in the near future is I'm currently using logarithmic transforms on the spectra, because this is just how the machine learning functions play nicely with more compressed data ranges. So if we can try to change the network architecture to allow for linear space spectra, this will hopefully greatly improve the accuracy, because a small uncertainty in the magnitude of the spectrum in logarithmic space can correspond to an order of magnitude difference in linear space. So that should hopefully greatly improve the accuracy. And we've got several methods of trying to do this right now. And then finally, we want to apply it to more complex models, because this is where we're going to start seeing the even greater speeds up, because we expect to see a fairly minimal increase in computational time for more complex models for machine learning, which means that as the traditional methods get more and more computationally expensive, this will become even bigger gap between our method and traditional methods. And we can get more useful information from it. And we also want to apply this method outside of Black Hole X-Ray Binaries, which is being worked on by Whyle and Josh, where they're doing prediction of atmospheric compositions for exoplanets using mass transition spectra, or predicting galaxy redshift. Thank you.
Brilliant. Thank you, Ethan. 28 seconds to spare. Any questions? Yes, Vinay, 1 second, just get you the mic.
So quick question. So you had a slide with 10 iterations and expect and 60 iterations. What's an iteration? What do you call an iteration?
In the expect software, it's just expect will update the parameters, and that's what we call an iteration. So each time the expect will update the parameters and calculate the fit statistic, that's one iteration. So we just do that 10 times.
So you're not actually waiting for it to reach a best fit or
No, not yet.
Just 10 steps.
Yeah.
Yes, one question here. Any online questions that are?
Hi, great talk. And how do you use the encoder together with the XSpec fitter?
So with expert, you can provide initial guesses. So we just generate the initial guesses using the encoder and then pass that into expect and then perform the iterations from there. And so that will, yeah, as we can see, it does help a lot with that.
Any more questions? Sorry, I haven't been looking up very much. Okay, well, let's thank Ethan again. Thanks for having you. Our next speaker is Arthur Whyle. Now, Arthur comes from the real Cambridge in the UK. Outside of astronomy, he enjoys reading and gaming. Actually, the only student this year who actually identified gaming as one of their hobbies. And he plays squash. During the summer, he's going to go traveling in Europe and meet with friends and stuff before he begins a PhD at the University of Portsmouth in the south of the UK. And what did you like during the US? And I really like going around cities, Seattle, New York, and Boston. Of course, the LA's giving me a good opportunity for that. And he's going to enjoy with going back with family and friends. He didn't mention cheap beer, so there we go. So take it away, on understanding the nature of the ultra steep spectrum diffuse radio source in galaxy cluster Abell 272.
Can you hear me? Yeah. Okay. Yeah, okay, so I'm going to be presenting my project that I worked on with Scott Randall on understanding the nature of the ultra-steep spectrum diffuse radio source in the galaxy cluster Abell 272. So, to start, I'd like to explain what we mean by diffuse radio sources in galaxy clusters. These are big, extended radio sources that can span hundreds of kiloparsecs or even megaparsecs. Typically, we find them in merging clusters, and they come in four main types. So here I'll give a brief overview of these four main types. So first, on the right-hand side, we have radio halos. These are observed in cluster cores and are thought to be caused by merger turbulence. Then over on the I said I got my left and right next up. Over here we have our other three types that are found outside cluster cores. So at the top we have radio relics. These are elongated along shock fronts and are therefore thought to be caused directly by shock acceleration in a merger event. Then we have radio phoenixes. These have more irregular, varied morphologies and are thought to be caused by the adiabatic compression of the intracluster medium as a result of a merger. And finally, we have AGN relics. These are essentially radio outbursts from AGN, and then over time, these radio lobes detach from their host galaxies and become these diffuse radio sources that we observe. So what makes ultra-steep spectrum sources special? Well, these are diffuse radio sources that they're much rarer and therefore not as well understood. And they have very steep spectra in their radio power laws of this form, where your flux is proportional to frequency to a power. They have spectral indices in the power that's less than -1.5, so these sources drop off in flux very rapidly as you increase in frequency. And by studying these sources, we can learn more about the life cycle of non-thermal particles that are emitted in these radio outbursts from radio galaxies and clusters, and also further study processes that occur in the intracluster medium that interact with these non-thermal particles. So I'm looking at this cluster Abell 272 that contains an ultra-steep spectrum source, gives some general properties. It has a radius of 770 kiloparsecs, a mass of 1.4 times 10 to the 14 solar masses, an average temperature of 3.1 kiloelectron volts. The cluster is located at a redshift of 0.087, so it's relatively close for a cluster. And to study the intracluster medium, we used an 18.6 kilosecond XOM Newton observation to look at the intracluster medium, which emits in the X-rays. And our goal with that is to determine the dynamical state of the cluster. In particular, we want to look for signs of it being a cluster merger. So here's a zoomed in view of the X-ray image of the cluster. The exposure corrected count rate image. And there are three main things to point out. At the top here, we have the cluster core, this bright peak at the top. Below it, we see another bright peak, which at first glance looks like it might be a second core. But after doing some spectral analysis of the source, we found it's actually an AGN that may well still be located in the cluster. Because this is an AGN, we treated it as a point source and removed it from any further analysis of the intracluster medium. And the other main feature in this image is this extended southern region of the intracluster medium south of the core. And this is our first main piece of evidence. This is the cluster merger. If the cluster was just an isolated system, you'd expect the ICM to be evenly distributed around the core, but because we're seeing this big elongated region, it's clearly a disturbed region and therefore a merger. We also looked at the thermal structure of the intercluster medium. So what we did, shown in this plot on the right, left, so we split it into 4 sectors, each with 5 radial bins. And we extracted the spectra from each of those bins and fitted it with a thermal Bremsstrahlung model. And using that, we can get the average temperature for each bin, which is plotted here with temperature on the y-axis and distance from the center of the cluster on the x-axis. And the main thing to note here in this plot is that the southern sector, plotted with blue points, is the hottest at all the distances. And what this is showing that this bright southern region is more energetic, and therefore it's probably been re-energized a bit by the cluster merger. So to recap what we've learned about the cluster dynamical state, we know that the intercluster medium is extended south of the core, and that region also happens to be hotter on average. So from that, we conclude the system is an ongoing cluster merger. Now, let's look at the radio source. So it has a steep spectra. Here we've got VLA and GMRT fluxes from 74 megahertz up to 1.4 gigahertz, and shown it's fitted with the radio power law. It has a spectral index of -1.9, so it's dropping off very rapidly as you go to higher flux, higher frequencies. And here is a 144 megahertz low-far image of the source, and you can see it has a double lobe structure. And because of that, we think it's likely that you could have an AGN at the center of those 2 lobes. And in fact, when we look at archival optical data, we find that there is in fact a galaxy right in the center of those 2 lobes. So we think it's very likely that there is an AGN inside that galaxy that is giving off these radio lobes. But also what you can see is that in the northern lobe up here, there is a fainter filament splitting off on the left-hand side. So it's not just a perfect double lobe structure. As for the source's location, here again we've got the X-ray image with the low-far contours overlaid. And you can see the source is located here in the southern extended region of the intercluster medium. Okay, so now to try and classify what the source might be. Well, we know it's not located in the cluster center, so it can't be a radio halo. We also note that the source isn't located at any clear shock fronts, so it's very unlikely it's a radio relic, and that just leaves radio phoenix and AGN relic, and in fact it shows properties of both types. So we're pretty confident that the radio emitting particles or electrons originated from an AGN in the center of the 2 lobes. However, it can't just be that, because it wouldn't have such a steep spectrum or this unusual structure with the filament off to the left. And we remember from earlier that it is located in this hot region of the ICM that is likely means it's been affected by the merger in some way. So we think that what we're seeing here are the AGN radio lobes that have then been partially re-energized as a result of the merger, like what would occur for a radio phoenix. So to conclude, we have found that Abell 272 is a cluster merger, and looking at the radio source, we found it has a double lobe structure. It's located in the hottest, most disturbed region of the cluster, and the likely origin of the source is that it's the radio lobes from an AGN outburst that have been partially re-accelerated by the merger. Thank you for listening.
Excellent, Arthur. Nice in time. Any questions for Arthur? Yes.
So what is the actual emission mechanism from the electron? Usually we expect to have, synchrotron radiation, but this has a spectrum which falls off even more rapidly than synchrotron. So what are those electrons doing?
Yes, so it is synchrotron radiation, but because of the way they're re-accelerated, that's what makes the ultra steep spectrum sources unique, is that for most diffuse radio sources, when they're re-accelerated, you expect to see the whole spectrum sort of increase in flux by kind of a uniform amount across all frequencies. But for these ultra steep spectrum sources, it only really increases in the for lower frequencies. And that's due, so in the case of a radio phoenix, that's due to the adiabatic compression. So I think there's probably some element of that happening here.
Any other questions for Arthur? Yes, Jeff.
Yeah, I was just curious, for the AGN relic interpretation, do you have any information to say how long to constrain when it would have shut off, to say something about the age of those lobes?
No, well, we can see, so for this source in particular, a typical AGN relic, you would have the lobes be detached from their host AGN. Here, it seems that they are still attached. There's maybe a little bit of a break between the two here, but they still seem to be attached. So it's not really a typical AGN relic, which perhaps suggests that it's a somewhat recent radio outburst that has then been affected by the merger.
Thanks. Great. Well, let's thank Arthur again. Now, unfortunately, our final speaker had a medical issue that meant that she had to return to Spain a week or so ago, and she is going to be joining us through Zoom. Do we know if we have Farah?
Hi, I'm really sorry, but Ethan, could you let me screen share?
Oh, I don't have permission.
No.
Actually, you should try it now.
Okay.
Let me just introduce Farah while that's getting sorted out. So her full name is Farah Puigdomenech. I mangled that a little bit. Sorry, Farah. She is actually originally from Spain, but spent time in Germany and grew up in the region of Barcelona. During the other work that she did in Southampton, she enjoys hiking, Latin dance, and she has an active interest in climate change. She plays field hockey, and during the summer, she's going to be going on an interrail trip in Europe. Now, those of you in the US probably don't know what that means, but it's basically you get this train ticket throughout the whole of Europe, and you just get train, and stay in the worst hotels in Europe, and for as little money as you can, and cheap beer probably facts in there. So what's she going to do next year? She's taking a year out, and she's going to be doing some advanced programming courses, and doing some deep diving into climate change science. And what did she find surprising or interesting here? And it was that they put ice in any drink. What did she miss? Spanish food and British humor. Certainly working with me, that's interesting. Yeah, unique humor for that. Anyway, is there anything unusual that she likes to do? And it is that she likes to read the last page of every book before she starts reading. Interesting. Okay, Farah, simulating the stellar galactic X-ray emission of cool stars from Exoplanet Habitability.
Well, hi everyone. I'm Farah. Thank you for the introduction, Jeremy. Today, I am going to talk about the work I've been doing this year so far related to the simulation of the X-ray emission of cool stars of our galaxy. Cool stars are stellar bodies that can have up to 1.3 solar masses that have a convective outer envelope. Depending on their mass, they can be fully convective, so the outer envelope takes up the whole star, or partly convective. The rotation of cool stars creates a dynamo in the convective layer of the star. This dynamo, via the shearing of internal material, creates a magnetic field, which rises to the surface buoyantly, creating a surface magnetic field. This surface magnetic field is responsible for the spin down rate of stars through stellar winds. Stellar winds are created through open field lines. So the open magnetic field lines, some material from the star tunnels through these field lines to the end of them and is ejected from the star, creating the stellar winds. And this ejected material creates a torque on the outer layers of the star, which causes the loss of angular momentum. The classical description of angular momentum loss rate for dipolar stars, so we don't take into account the complexity of the magnetic field of these stars, is shown here in the slide. And the angular momentum loss rate is proportional to the cube of the angular momentum of the star. Following this classical description, we would think that the rotation period of stars follows the Puigdomenech law. Following this trend that you can see here, this top branch, which is also called the slow rotator branch. But recent open cluster observations have shown that some stars barely lose any angular momentum. So the rotation period stays pretty much stable for a long period of time, which are the stars that you can see here piled up in a horizontal line at really short rotation periods, which are also called the fast rotator branch. So after these observations, the Garofalo et al. 2018 spin down model was created that tries to describe this bimodality seen in open cluster observations. So they take the classical description of the angular momentum loss rate, and then they multiply it by an element that takes into account the complexity of the magnetic field. It was found that the complexity of magnetic field can have a huge impact on the angular momentum loss rate. So if stars have more complex magnetic field morphologies, the stars are going to lose angular momentum less efficiently. Here it's an overview of what I've been telling you so far. So the rotation period of stars is the one fueling the dynamo that creates the magnetic activity of stars. And this magnetic activity is the one creating the magnetic braking, or also spin down, that affects the rotation of stars. So if we have a higher rotation, then we're going to have a higher magnetic activity, and that's going to affect the rotation again. So it's a self-regulating mechanism. So now we've talked about the importance of magnetic fields on the spin down of stars, but the surface magnetic fields are also really important for the X-ray and EUV emissions. The X-ray and EUV emissions are the main drivers of atmospheric loss in exoplanets because they heat up and evaporate planetary atmospheres. So now we can see that it's really important to know the rotation period of stars and how the rotation period affects the magnetic activity, and this magnetic activity is the one accountable for the X-ray emission. So we want to know the relationship between the rotation period of stars and the X-ray emission, so we can infer one from the other. So Wright et al. 2011 found a relationship between the rotation period of stars and the X-ray emission. If we have a star of a specific mass, stars that rotate faster are going to give out a higher X-ray luminosity until they hit the saturation point, which is this point here. And after this point, even if the star rotates faster, it's not going to output a higher X-ray emission. We're going to have a constant X-ray emission after the saturation point. So this year, what I've been working on is a combined model that combines the Garofalo et al. 2018 spin down model and the Wright et al. 2011 X-ray rotation period to calculate the rotation period and X-ray emission of cool stars from basic stellar parameters. The basic stellar parameters are mass and age, which were taken from the GAMS dataset, which is a synthetic dataset of stars of our galaxy that was created to be able to know which stars would be observable with Gaia. We chose this data set just because it has it's the only data set up to date that has specific ages for all the stars in our galaxy. And then the initial rotation period was taken from a resampling of points of the H per cluster, which is a cluster that's 13 million years old, and we think it's a good representation of our galaxy at that age. Then from this basic stars parameters, we get the rotation period of the stars. And then with the rotation period and basic stellar parameters, we can infer the X-ray emission following the Wright et al. 2011 relationship. With this X-ray emission from our pipeline, we can also get the XUV spectra from the emission measure distributions of Wood et al. 2018. And with the X-ray emissions, calculated X-ray emissions from our GAMS data set, we can also get the galactic X-ray background using the 3D extinction maps from Berkeley et al. 2022. So here are some results we get from the pipeline. So our model calculates a rotation period of stars as a function of mass and age. And we get this from basic stellar parameters, as I said, mass, age, and initial rotation period, which other models are not able to do. From the rotation periods, we can also infer the X-ray emission as a function of rotation period and mass of the stars. And this is also an example of what we can get from the pipeline, which is a spectra of a star of 0.15 solar masses. For future work, we want to be able to calibrate the rotation model to make reliable predictions. And we also want to use our results to create a map of the stellar contribution to the celestial X-ray background. So here are my conclusions. I presented to you the pipeline that combines the Garofalo et al. 2011 spin down model and the Wright et al. 2011 coronal emission rotation period relationship. This pipeline outputs the rotation period, X-ray emission, attenuated X-ray emission, and XUV spectrum of all the stars, all the cool stars of our galaxy from basic stellar parameters. And the results are going to be very useful for exoplanet studies and also to probe the stellar contribution to the X-ray background. Thank you for listening to my talk, and I'm open to any questions.
Thank you very much, Farah, and plenty of time. Yes, any questions for Farah? Anything online, Federico? So Farah, regarding the X-ray background, what do you expect to see from the star X-ray background in comparison to other sources of X-ray background that we see in the sky?
Yes, so there's been a lot of work behind this, and we are expecting that the most luminous sources from the X-ray background are going to be AGNs and other really bright sources. But we also think that the stellar contribution to the X-ray background is good. It's not going to be as luminous as other sources, but it's going to be a notable enough contribution to what we're going to be able to see in missions that study the X-ray background of the galaxy.
Okay, thank you. Yeah. Any other questions for Farah? Yes, Jack.
Hi, Farah. I just wondered if you could say a little bit more about the applicability to exoplanet studies.
Yes. So basically, knowing how stars evolve over time, and if we know how stars and their rotation evolves over time, as you've seen here, we can also know how their emissions, X-ray emissions and UV emissions change over time. So if we know that, we are going to be able to know which stellar environments are going to be feasible for exoplanet habitability. So if we are able to know in advance which stellar environments are going to be habitable or hospitable, then we are able to point all our efforts to the places in our galaxy that we think that we're going to be able to find some exoplanets that could possibly contain life. So we don't have to just guess where we point our telescopes and just hope that there's a star that has exoplanets around them that can perhaps contain life, and their X-ray emissions haven't just evaporated and heated up all the atmospheres.
Hi, Farah. Thanks so much. This is Morgan. I'm curious about applying the sort of pipeline that you developed to the known exoplanet host stars and looking at their sort of predicted X-ray emission and whether you can map that to, say, like predicted mass loss rates from those planets. So are there systems that we haven't surveyed for excess atmospheric absorption that your pipeline predicts are particularly strong candidates for that sort of thing? I wondered if that's an exciting extension of what you're doing, or if that's something you've done already. Or...
Okay, so I'm going to repeat the question just in case I got it wrong, but basically you are asking if my pipeline could also predict the evolution of the evaporation of exoplanet atmospheres.
I think so, yeah, and that we have all these host stars where we measure some of these parameters that might be the input for your pipeline.
I think that's something that our pipeline isn't doing right now, but it's a good, it could be a good addition. So if we know what the X-ray emission of stars is at one point in time, and we can also infer the whole evolution of this of these emissions, then obviously we could perhaps quite easily, I don't know how easily it is to calculate the atmospheric loss rate, but it's something that we had a name for this project to start with this, but also put a lot of effort also into studying the atmospheric loss of exoplanets, which we haven't managed to do because this has taken a lot of the time, but it's something that we like the group that I've been working with, they've also been working a lot with with the environment of exoplanets and modeling their atmospheres and atmospheric loss. So it would be something that we could also add to the pipeline.
Thank you so much.
Okay, well, we are out of time, so that concludes the Southampton students' year and presentations, and let's thank all the speakers again. Thank you very much.